Okay, in this last video for chapter 20, we're going to look at electric fields, electric field lines, and also a little bit about electric potential or voltage. We know that when a charge comes near another charge, it feels a force. And we say that's because every charge is surrounded by an electric field. Every charge is surrounded by an electric field. And that electric field exerts forces on other charges. If I was to draw a picture of an electric field, I would use something called electric field lines to represent it. If I have a positive point charge like this, we know that any other positive charge that I bring near it will feel pushed away from that positive charge. So if I bring a little positive charge over here, it's going to feel a force this way to push it away. So electric field lines are drawn in the direction of force on a positive charge. So anything close to this would get pushed away. So our electric field lines point like this. And how many we draw is a little arbitrary. I usually draw 8. And of course, that's really 2-dimensional, but if you can think of it as 3-dimensional, those electric field lines will point out in every direction. And that tells me that if I'm a little positive charge and I'm right here, I'm going to feel a force away. Okay? Electric field lines, or electric fields, not just the line, but the electric field points in the direction of the force on a positive charge. So if you have a positive charge and it's in an electric field, it's going to feel a force in the same direction as those electric field lines we drew. If you happen to be a little negative charge, well, of course, a negative charge is going to be attracted to this positive. So it actually feels a force in the opposite direction. Okay? So the force is in the same direction as the electric field if you're a positive charge, but the force acting on a negative charge is going to be in the opposite direction. Okay? That makes sense. Now let's think about it. Let's draw what the electric field looks like if you happen to be a negative charge. If you happen to be a negative charge, well, think about it. If I put a little positive charge up there, it's going to feel a force this way. And a positive charge over here will feel a force this way. And a positive charge, in fact, positive charges are attracted toward negative. So when we draw electric field lines for negative point charges, they look like this. And of course they look like that because we know a positive charge will feel pulled that direction. Whereas a negative charge always is against the electric field, it feels a force that direction. Okay? So we can see how the direction works. The direction of the electric field is the direction of force on a positive charge. Now, the actual size of an electric field is really easy to calculate. The strength of the electric field, or the size of the electric field, is given by this formula. And it is a vector field. The electric field has direction. And it is simply equal to the force, which also has direction, divided by the charge. If we think about units, we measure force in newtons. We measure electric charge in coulombs. So electric fields have units usually written as newtons per coulomb. For example, a 2 coulomb charge feels a 50 Newton, make it a positive 2 coulomb charge, feels a 50 Newton force to the right. Let's see if we can calculate the electric field at that point. I know the electric field will be the force divided by the charge, so 50 newtons, 2 coulombs. So it looks like the electric field is 25 newtons per coulomb. It says it feels the force to the right. Well, if a positive charge feels a force to the right, then the electric field points to the right. Now, I can change that problem. If a negative charge felt a force to the right, well, if a negative charge is being pulled to the right, that means a positive charge would have been pulled to the left. It would have changed the direction if we had changed that charge, okay? Now, another way we often use this is we'll get things that say something like, well, we want to find the force. Well, with just a little rearranging, we can see that this formula is equivalent to saying that the force is equal to QE. A negative 5 coulomb charge is in an electric field E, which is 75, no, let's not do 75, let's do 70 newtons per coulomb to the right. What force acts on the charge? Well, the electric field points to the right, but since they tell me that my charge is negative, I know that it feels a force to the left because negative charges always feel a force opposite the electric field. If it was a positive 5 coulombs, it'd feel a force to the right, but it's negative, so it feels a force to the left. How large a force? Well, that force is QE. So I've got 5 coulombs. I don't care about the negative on this part. I'm just trying to figure out how big the force is. 5 coulombs times there are 70 newtons per coulomb. 5 times, that is 350 newtons. And we already determined that since the electric field points right, the force is to the left. Okay, so as far as doing problems, I think that's the only problems you really need to be able to do. You just want to remember that the force on a positive charge is the same as the direction of the electric field. the force on a negative charge is opposite the direction of the electric field. I'm going to write just a little bit more about drawing electric fields. Electric field lines obey some certain rules. One rule is that they begin on positive charge and they end on negative charge. Two, they never cross. Three, they're closer together. Where the field is strongest. Where the field if I had, say, a positive charge here, so that's plus 2 coulombs, and a negative charge here, that's minus 1. We would expect lines to go from positive towards negative. We would also expect this charge to have more lines because it has more charge. The number of lines does depend on how much charge we've got. These are going to kind of bend a little. And over here, there won't be as many, something like that. I put 4 lines here, but I put 1, 2, 3, 4, 5, 6, 7, 8 lines here. Twice as much charge, twice as many lines. They point away from a positive and they point towards the negative. You'll notice that here, the electric field on this side is going to be a little stronger than the electric field over here. These lines are closer together. Okay. All right, our last idea in this chapter is about electric potential. Electric potential is what you commonly call voltage. Okay. It's not quite the same thing as electric potential energy, but it's really closely related to the idea of electric potential energy. So, electric potential or voltage. Electric potential is one of those things that applies to static electricity, but it also applies to current electricity. And we'll really talk about voltage a lot more when we're talking about current flowing. But we do want to define it in this chapter. When a charge moves in an electric field, that means that the electric field does work on the charge. What Will that make sense if we go back and we try to remember earlier in the semester? We said work is force times distance. Well, if you're a charge and you're in an electric field, you feel a force. So if you actually move through some distance, that electric field did work on you. For example, if you had an electric field that was pointing this way, and you had a positive charge and it moved from here over to here, well, work was done on it because it moved, right? When we do work on something, one of two things happen. We either give it kinetic energy or we give it potential energy. Remember back when we were talking about the work done in lifting up a box and setting it on a shelf? Well, we were doing work against gravity and we gave it gravitational potential energy, okay? So, voltage by definition equals the work done on a charge divided by the charge. So it's not energy, but work has the same units as energy. We define 1 volt to equal 1 joule per coulomb. Really important probably that you remember what 1 volt means, because there's 2 ways to think about it. If you have a 12 volt battery, that battery does 12 joules of work on every coulomb of charge that flows through it. A 12 volt battery does 12 joules of work on every 1 coulomb of charge that flows through it. Another way to think about that same thing is that when a coulomb of charge goes through the battery, that coulomb of charge gains 12 joules of potential energy. So when you connect a 9 volt battery, every coulomb of charge that flows through it has 9 joules of work done on it, and every coulomb of charge that flows through it gains 9 joules of electric potential energy. The whole purpose in putting batteries in circuits is to give those electric charges energy to keep them flowing. Okay? So you can almost think of it as being when something goes to the battery, it's like it gains potential energy, and when it flows through the circuit, it loses potential energy back down. So voltage is just telling us how much work was done on every joule and how much potential energy is gained by the charge. Okay, all right, that's the end of chapter 20. I believe next chapter is going to be about electric circuits. So I'm going to stop right here.